Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. In today's session, we are going to look into approximating a linear regression, meaning I want to use something we call the least squares approximation of a system of linear equations. I went over that in probability and statistics, and we can derive the equations easily. But here we are going to look at it from, in fact, it's the same problem, but we are going to look at it from a different perspective, from the point of view of linear algebra. And the problem would be you have a system of linear equations, AX equals B, and you try to solve it and you don't get any solution. There are no, so for example, you get three equations in two unknowns, but so you have an extra equation here, like it's over determined type of problems. And when you solve, you cannot find the values of x and y that satisfy all the right-hand sides. So what do? You say, okay, life is full of, uncertainties and, some problems you cannot get like a precise answer. So what you can do is to find the best approximation. What are the values of x and y or x, y, z or what have you that would get as close as possible to the right-hand side? And what's the meaning of as close as possible? Some of them will overshoot, some of them will not reach. So some errors would be positive, others would be negative. You can take the absolute value to see which system is best. We don't like to work with absolute value functions. So instead, we square them. When we square them, all of them would be positive. Because why I'm saying we have to do something to the signs. Because if I get a point that is overshooting me and higher than the right-hand side by a huge value, and the other point is below the right-hand side with a huge value, and when you add them up, you may get zero or something very small, and you say, oh, that's a great equation. No, it's not. So we don't want the positive and the negatives to cancel each other. So as I said, usually with the first thing to think about is, oh, absolute value. But the absolute value is not easy to deal with as a function. Squares is better. So that's why we use the least square errors or the least square approximation for that. And the situation can be found, for example, if I have the vector b, which is the right-hand side values, is a vector here, but the column space of A is somewhere here. So this is AX and this is B. Okay? So we say, well, if B was in the column space of A, meaning I can write B as a linear combination of the columns of A, these two lines would coincide. But if I have B here and I want a value in my column space to minimize or to approximate B, I say, how do I get from this point to that line? What is the closest distance? Yeah, everybody said it in one voice. It is the perpendicular distance, right? So I'm going to find, if I'm going to draw a line, well, I didn't need to extend it. I thought it was. If I draw this line perpendicular to it, so I have minimized the error. I get as close as I can to from my column space, the column space of the matrix, to vector V. I'm writing them away from each other so you can see. Notice this is the project, that's the orthogonal projection of B onto AX, which is the dot product of B with the unit vector of AX times the unit vector of AX. But this part, remember we did that in the dot product, is the difference between the two. It's B minus A sub x. And that's what I can minimize if I make that perpendicular. Wait a second. That's the column space of A. Remember when we were discussing the 4 subspaces of a matrix, and we said one of them was perpendicular to the column space of A. Does anyone remember what was that? The left null space, the null space of A transpose, which means I can say that A transpose, notice when you do A transpose, A dot B minus AX, you have to do the transpose of that because you are multiplying a row by a column, right? So A transpose times B minus AX equals 0. This is the equation that we will be using. Of course, we can simplify it by distributing the A transpose. So you get A transpose B minus A transpose A X equals 0. I'm going to add A transpose AX to both sides, but I'm going to leave this on the left. It doesn't matter really, but that's how you will see it. And you say, where does the transpose and the stuff come from? This is the equation we are going to use to solve. Some people will say, okay, why don't you solve for x? Yeah, I can multiply both sides by A transpose A inverse times A transpose A times x equals A transpose A inverse times B. Oh, but A inverse times this guy, when you take the inverse, they invert, so they become, so when you multiply A transpose A by A transpose A inverse, they cancel each other, and these two guys give me I, which is the one in matrices, and you get my X vector. The closest to that is A transpose A inverse times B. So you can use either equation. This means I'm going to solve the left-hand side by itself and then the right-hand side by itself and then do the inverse of that times that, or here you do it again. It's the same idea. Oh, I'm sorry. There is an A sub A transpose here. Right? We multiply this by A transpose. Why didn't I write A transpose? I don't know. Okay, let's take an example and it would make our lives easy. Here are 3 equations and 3 unknowns. If you try to solve them, unfortunately, you won't get that. Try it as if you want, but I guarantee you there is no solution for that system. So this is matrix A. Let's do matrix A transpose to save time. So A transpose would be the coefficients of x and y. 2, 1, 2, 1, negative 1, 3, negative 1, 3, 4, 5, 4, 5, times matrix A. So this is A transpose times A. 2, 1, negative 1, 3, 4, 5. This is a 2 by 3, and this is a 3 by 2, so we end up with a 2 by 2 matrix. To get the first element, we multiply these two. Notice it's the same number, so it's like 2 square plus negative 1 square plus 4 square. So 4 plus 1 is 5 plus 16 is 21. If I want this entry, first times second, you get 2 minus 3 is negative 1 plus 20 is 19. This element is 2 minus 3 plus 20. Again, it's the same exact thing. They always be the same. It will always be a symmetric matrix. And then finally, the last element, you get 1 plus 9 is 10, plus 25 is 35. This is ATA. Next step is to get ATA inverse. ATA inverse. How do we invert this matrix? We know that what we need to do is to interchange these two elements, multiply these two by -1, and then divide by the determinant. So the determinant here equals 21 times 35 minus 19 squared. 20 times 35 is 700, and another 35, it's 735. 19 squared is 361. So this is 4743. 1 over 374. You interchange those and you multiply the others by -1. You don't interchange them, even though in this case it doesn't matter, but we don't interchange it. That's ATA inverse, okay? Now, in the right-hand side, I have A transpose times B. So let's do that on the side. A transpose is 2, 1, -1, 3, 4, 5. 2 times 3, we multiply it by 3 by 1. So we end up with a 2 by 1. 4 minus 1 is 3 plus 4 is 7. 2 plus 3 is 5 plus 5 is 10. So, notice, this is ATA inverse, and this is ATB, A transpose B, which is the 710. So I'm going to multiply that by 710, and that will give me X. So X equals, okay, I forgot to multiply, so let's multiply outside 3 by 1 over 374. Okay, 35 times 7 is 245, minus 190 is 55. 21 times 10 is 210, minus 19 times 7 is 133, 747, 77. You can see that these numbers are divisible by 11, and 374 is also divisible by 11 because 3 plus 4 equals 7. So we know that, it's 34 times 11. So if I divide by 11, I get 4. I get 5 over 34. And when I divide that by 11, I get 7 over 34. Meaning X is this, Y is that. I don't know why is that. Okay. So if I want to calculate the error matrix, which is B minus AX, it would give me, B is my estimate, and AX is the actual number. Okay, so, or you can look at it, B is this. B is this, and AX is my estimate. So let's do this. Let's say, for example, it doesn't matter because at the end of the day, we are going to square and sum them up. We want the least sum square. So I'm going to say 2 minus, and then between parentheses, I'm going to say 2x, which is 110 over 374. Well, I could have used that. Okay, it doesn't matter. So I'm going to say plus y. I'm going to say plus 7 over 34. I get 1.5. So the error here is 1.5. How about the error here? 1 minus, and then -5 over 34 plus 21 over 34. I get 0.529. And then here I get 1 minus 20 over 34 plus 35 over 34 equals negative 0.618. So the sum of E square is 1.5 square plus 0.529 square plus 0.618 square equals 3.757. No, see, that's impossible. That cannot be even 3. I didn't multiply. No, 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 no. This is 2.25, and these are less than 1 each one. You cannot get that high. 1.5 square plus this guy square plus, probably clicked the wrong button. Yeah, 2.149. Yeah, that makes sense. No, it doesn't make sense. Wait a second. It's probably because of the negative sign plus this guy square plus 2.25, which is 2.912. Yeah, that makes more sense. Because this is 2.25, and that's a quarter, so that's 2.5. And this is like 0.4, so 2.5 and 0.4 is 2.9. Yeah, makes sense. I don't know what. I can't use calculators. Horrible. Okay, let's take another example. And this example, it's a little different. I want to use the common ideas, the least squares, and I want to find the value y equals mx plus b. So I want the slope and I want the y-intercept. And this, of course, is not a straight line since 1 is 2 and 2 is 2. So there is a horizontal piece. It's not a line. But if I want to write it like that, I would say, for example, the first equation would be 1 y equals 0 times m plus b. The second equation would be the 2. So this is basically 1. And then this would be 2 equals 1 times m plus b. And this is 2 equals 2m plus b. And this would be 4 equals 3m plus b. And 5 equals 4m plus b. So if I want M and B in one matrix, the matrix A here would look something like that. 0, 1, 2, 3, 4, 1, 1, 1, 1, 1. So I'm going to use the same idea. A transpose times A, and then I take the inverse and multiply it by B, and B here is this matrix. So A transpose 0, 1, 1, 2, 3, 4, 1, 1, 1, 1 times 0, 1, 1, 1, 2, 1, 3, 1, 4, 1. And when I multiply those, I get a 2 by 2 matrix. Notice that the first one is basically I'm squaring these numbers. So 0 squared plus 1 squared is 1, plus 2 squared, that's 5. 5 plus 9 is 14. 14 plus 16 is 30. When I multiply by this column, I'm simply adding them because I'm saying 0 plus 1 plus 2 plus 3 plus 4, that's a 10. And here it's the same thing, 0 plus 1, that's a 10. And this is just the sum of the values, which is 5. And when you study probability or statistics and you are doing regression, you may see this equation written as this is the sum of x squared. You see the x's the x's here were 0 squared plus 1 squared plus 2 squared, which is the 30. And this guy is the sum of the x's. And this is just the number of points, n. Think about that, look it up, and then see how from here, we get the equation of, in fact, we are going to use the calculator and try to find the best line that fits the data, and hopefully, if we didn't do errors, we'll get the same result here. So having said that, so this is the left-hand side. I want to get this guy or the inverse of that guy. Delta here, or the determinant, is 3 times 5 minus 10 times 10 equals 150 minus 100 equals 50. So 1 over 50. I'm going to change that. So these are 5 and 30. Multiply these by -1. So it's -10, -10. That's the left-hand side. That's ATA. I'm sorry. This is ATA inverse. Okay? Then we are going to multiply this thing by AT times B. A transpose is 0, 1, 2, 3, 4, 1, 1, 1, 1, 1, times the vector B, which is 1, 2, 2, 4, 5. And that will give me a 2 by 1 matrix. 0 plus 2, 2 plus 4, 6, plus 12, 18, plus 20, 38. And then this is the sum, right? 1 plus 2 plus 2 plus 4 plus 5. So that's what, 14? 4 and 4, 9, 14. So I'm going to multiply that by 38, 14 to give me m on the top and b at the bottom, mx plus b, right? Okay, so 5 times 38 is 190, minus 140 is 50. But 50 over 50 is 1. Instead of saying divide by 50, it's 1. The second row, so m is 1. And the y-intercept is -380 plus 420. So that's 40. 40 over 50 is 4/5, or 0.8. So I get y equals, m is 1, so x plus b plus 0.8. And again, if I substitute for x's, for all the x's, when x is 0, I get 0.8 instead of 1. When x is 1, I get 1.8 instead of 2. When it's 2, I get 2.8 instead of 2. When it's 3, I get 3.8 instead of 4, and 4.8 instead of 5. So the errors here I have, for example, 0.2, 0.2, -0.8, 0.2, 0.2. So in any numbers with x's and y's, you will see that if I add all the deviations, I get 0. That's why I don't know how to take the best line. Any line that I draw between the x's and the y, the sum of the deviation definitely has to be 0. In fact, I know that this line has to pass through the average x and the average y. Again, this is beyond the scope of this course, but if you think we have 5 values and their sum is 10, so x bar is 2. For the y, the average, I have 5 values. We said their sum is 14, right? And 14 over 5 is 2.8. Now, if I substitute x bar is 2. 2 plus 0.8 is 2.8. So it's always going to satisfy that. That's definitely if it's a straight line. The sum square of the error, so the summation of the error would be 0.2 square plus 0.2 is 0.04 plus 0.04 plus 0.64 plus 0.04 plus 0.04. That would be 6470, oh, wait, 1680.8. By the way, I know it's beyond the scope of this course, but if I divide the sum of these deviations by n minus 2, where n is the number of data points, I get the variance in the data, and the standard deviation is the square of the variance. So let's try to make sure that we didn't do any error. So if I take the square root of 0.8, which is the summation of error squared, and I divide, oh, I'm sorry. No, it still has to be, divide that by 3, and then take the square root to get S. I get S equals 0.5164. Now, I want to check that. So I'm going to go to my stat menu, and I enter the x's 0, 1, 2, 3, 4. Oh, 4. And then I go to the y. Yeah, I want to do some exercise, so I'll go to the y. When I come back, I'll continue. Okay, I'm sorry, a horrible dad joke, I know. 1, 2, 2, 4, 5. And here there is nothing, of course. Okay. If I go back to stat and go to calc and select linear regression, AX plus B or MX plus B, you see A is 1 and B is 0.8. In fact, if I go, that's not what I wanted to do. I wanted to go to tests and something you're not going to worry about, but I'm going to go to the linear regression t-test, and let's look at what we get. Okay, let's go to calculate. Forget about that. We are not going to worry about it. Calculate. I still get degrees of freedom. It's called 3. That's why I divide by 3. Degrees of freedom in that straight line is the number of data points minus 2. Again, A is 0.8 because here it says A plus BX. So this is the y-intercept. That's the slope. So they are inverted here. You get the 0.8 first and then the 1. But go to the S. Hopefully we didn't try it. Yeah, 0.51639. Again, this is not a statistics class. I know that. I just want to draw your attention is that we are doing the same work from 2 different perspectives. One of them, I'm dealing with the summation of x squared, the summation of xy, the summation of x's, the summation of y's, and one I'm using a matrix, and it's transpose and the inverse, and both of them. That's the beauty of math, how to connect different subjects together and see how, and we included geometry and stuff to understand the dot product, and all of them lead to the same final answer. I hope this was nice. Next time we are going to look at the same type of problem, but from a slightly different perspective. We are going to use a different approach. I hope you like it. Thanks very much for watching. If you have any comments, please let me know. Otherwise, I wish you all the best and hope to see you soon.